So the classification of matter. What is matter? It's a different question than what's the matter. What is matter? Matter is anything that occupies space and has mass. So if you think about putting stickers on stuff, which was really fun when you're little, it's still kind of fun. Anything you could put a sticker on, that's going to be matter, right? There are also things that you can't put a sticker on that would be matter. Can anybody think of anything? A liquid, yeah. So you can't really stick a sticker on water, right? But water occupies space and has mass. What about air? We don't consciously think about air very much because we can't see it, and we only feel it when it gets moved against us. But this room is full of air, thank goodness, and it occupies space, which, you blow up a balloon. What's in the balloon? What's pushing it out is air, right? And it has mass. So air is also matter. What's something that's not matter? Space. Because most of space has nothing in it. Yeah. What about love? Does love matter? Love matters, but love isn't matter, right? Energy. Energy is not matter. So there are some things that are very real that are not matter, but most of what we encounter is matter, and that's what we're studying in chemistry. And one of the things we do in science is we categorize and classify things. We're looking for, well, what do these things have in common, and how are they different from these other things? It's not unlike, games that small children play with, their blocks, right? Well, let's put all the red blocks here and all the blue blocks there, right? You can classify things in many different ways as well. So if you think about vehicles, there's a lot of different ways you could classify them. You could put them in groups by color, or by size, or by what type of fuel they use, or by how many wheels they have, right? So there's different ways of categorizing the same group of stuff. So we're going to look at two ways of categorizing matter, according to its state, its physical form, and according to its composition. What are the things that are in it? So in this section, there's the picture slide, and I'm basically going to talk about all the next slides in the picture slide, but then you can go read those later. So I'll just skip through those quite quickly when I'm done with this one. So the three states of matter are solid, liquid, and gas. And one thing that we're familiar with in all three of its forms is water. So, water that you might drink, what we call water, is a liquid, right? But you stick it in the freezer and it gets hard, becomes a solid, and we call that ice. If you heat water up, it will evaporate or boil and go into the gas state and float away. So that's the gas state. The states of matter change from solid to liquid to gas with increasing temperature. And you decrease the temperature and they go from gas to liquid to solid. And what's different is the relationships between the particles. So when you melt something, it doesn't change the individual building blocks, atoms or molecules that compose that substance. All we're doing now is here, in the solid, the particles are touchingly close and they're not moving relative to each other. So if we talk about the three states of students, right now you guys are in the solid state. Because that person sitting next to you has been sitting next to you for like the last hour, right? You haven't moved relative to them. Now, nobody in here has been completely still, because that would mean you weren't breathing, and that would be tragic. Some of you are fidgeting more than others, and that's fine. I don't care about fidgeting, but we're all moving, right? And we'll learn later that the particles in here are not stationary, but they're not moving relative to each other. They're essentially wiggling, right? So a solid is going to have a constant or definite shape and a definite volume. Think about an ice cube, You pop it out of the ice cube tray and you stick it in a bowl. Does it change shape? No, it's the same shape as it was before. And it's the same volume that it was before. What happens though, sits in the bowl on the counter, begins to melt. It turns into a liquid. And then its shape will change. Because in the liquid, the particles are still touchingly close, but now they can move around each other. And so the liquid state of chemistry students is in lab. We're all still here in the same space, but now we'll be walking around. And you won't always be in front of or behind that person that you're in front of or behind right now. So here they're moving around. The volume, though, is going to stay the same. You put a cup of water in a big bowl, and it changes shape. You pour it back into the measuring cup. It's still the same volume, but its shape will change. You heat things up more, and you get the gas state. And the gas state of students is when class is finally over, and she says, I can go home, and everybody goes out the door, and you go off in all different directions, and you probably don't see each other until Tuesday. You come back in and become a solid again. In a gas, the particles are far apart from each other. And that distance between them can change. So the volume can get bigger as they spread apart, or it can get smaller as they get closer together. The volume can change, and the shape can change. So solids, liquids, and gases, we need to understand their shape and volume, which ones can change and which ones don't change. So those are the things I mentioned about solids. We can, of course, categorize solids also as crystalline or amorphous. And so in a crystalline solid, a lot of these solids do actually look like crystals. The particles have a regular repeating pattern. So diamond is an example of a crystalline solid. The atoms are arranged in a very particular way. Okay, and this would be like, kindergarten class, and they all came in and they sat at their desks, right? Just like you guys. And you're in rows. There's an order, right? But then it's story time, and the teachers come up and sit on the floor. Do they sit in rows? No, they just plop down all over the place. That's like an amorphous solid. Amorphous, without shape, it doesn't have an order. There's no pattern. The particles are just kind of jumbled together. And whether it's amorphous or crystalline has an effect on the characteristics of the solid. So crystalline solids, table salt, diamond, glass, and plastic are examples of amorphous solids. Liquid, I mentioned those things. Gases, I talked about the changeable volume. Here's some good pictures. So this is like a piston assembly, so you can push down on this. And this is a solid. In a solid, the molecules are already as close as they can get. And so if you try to squish them together, they're like, good luck. We're already touching. We can't get any closer. You can put a lot of pressure on that, and it's not going to change its volume. A gas is very different, though, because there's lots of space between the particles. And when you put pressure on the gas, you can push the particles closer together. So gases are compressible. Just another way of saying they can change volume. This is another place where I'm going to talk about all of these things and then the slides with all the words. We'll just go through quickly. So that was classifying matter by its physical state. Now we'll look at classifying matter according to its composition. So the first question we can ask is, does it have a variable composition? Is the composition always the same, or can it change? Well, if it's all the same, it doesn't vary, then that's known as a pure substance. Water is an example of a pure substance. Water always has the same particles in it. They don't change, right? Well, why do different waters taste different? Well, because we're not drinking pure water. We're drinking water that has trace minerals and stuff in it, and that's what gives you the different taste of water. But water itself doesn't really have a taste, and it's just like here, all these little water molecules. So the pure substance, the next question we can ask, can we separate into simpler substances? Can we break this apart? And for water, the answer is yes. If you pass electricity through water, you can break it into hydrogen gas and oxygen gas. And that's something you can do at home. It's not really that exciting, but drop a 9-volt battery into a glass of tap water. Wait a few minutes, and you'll see little bubbles forming at the terminals. And that is electricity decomposing the water. Don't worry, you're not destroying water. It'll come back together in a reaction somewhere else. This sort of thing happens all the time. But you can separate it into hydrogen and oxygen gases. But other things that are pure substance cannot be. So the compound is going to contain 2 or more types of elements, and an element is just a single type of atom. So an example is helium gas. Helium gas, like used in the Goodyear blimp, it just has helium atoms. They're not connected to each other. They're not connected to other atoms. They're just individual helium atoms, and you can't separate those. Kind of like Legos, right? You've got this thing. Oh, I can separate it. I can take the blocks apart. Okay, well, so maybe that's a compound. But you get that block. So maybe you've got a little 2x2 red Lego brick. Can you separate that into smaller pieces with your bare hands? No. In a chemical process, you cannot. So that would be like an element. Now, could you take a saw to the Lego brick or a sledgehammer and make it into smaller pieces? Well, sure you could, but that's not normal, right? If you think it's normal, maybe we should have a conversation later. But that would be like nuclear chemistry. So what we'll learn is atoms actually can be taken apart in smaller pieces. But that's nuclear chemistry. That's a special kind of thing. It's not what normally goes on. All of this stuff is talking about just a chemical reaction, which is like Legos in your hands. You can't break up the Legos, not the individual blocks. So these are going to be the same. It's always the same composition. Helium is always helium atoms. Water is always 2 hydrogens stuck to 1 oxygen. Always. Because if you have something different, like 2 oxygens and 2 hydrogens, now you've got hydrogen peroxide. It isn't water anymore. Well, what if the composition is variable? Then that substance is a mixture. It's got 2 different substances in it. And so then we can look at, well, is it uniform throughout? Does it look like it's all the same, or does it look like it has different parts? So heterogeneous, these are prefixes. We use a lot of prefixes in the English language and in science. Hetero means different, and homo means the same. So a heterogeneous mixture has different parts to it. An example of this is sand and water. So you can kind of imagine this. Take a glass of water and you pour some sand in it and you stir it up. And then you stop stirring, and what happens? All the sand sinks to the bottom, and you've got wet sand down there, and you've got water up here. So there's the water, and then there's the wet sand part. It's not the same throughout. If you took water and put some sugar in it, or salt for that matter, and stirred it up, the salt or sugar would dissolve. You wouldn't see anything sitting on the bottom, and the composition would be the same throughout. The top would be just as, well, let's forget the salt. The top would be just as sweet as the bottom. It would taste the same all the way. Here, if you were tasting this, the top would probably taste okay, and the bottom would taste really, really crunchy. So a homogeneous mixture is more like the sugar dissolved in water, or here, a fancy form of water, tea, right? So you put sugar in your tea, it dissolves. So heterogeneous examples would be like vegetable soup with it's got chunks in it and stuff. Or chicken noodle soup, it's got chicken pieces and noodle pieces and broth. That would be heterogeneous. A homogeneous soup would be something like, tomato soup, right? Or cream of something where it's been all blended up, right? And it's just all the same. You can't say, well, I'm going to pick the carrots out of this because they're all blended together. So those are the words. It's just so much easier to talk about it with the pictures. Okay, here's some more pictures. So in these panels here, A, B, and C, a blue circle represents one kind of atom, type of element, and a red square represents a different one. Question is, which of these images represents a pure substance? In a pure substance, the composition is the same. Doesn't have a variable composition. A is going to be our pure substance. Because each of these, they'd be molecules, I guess, is a blue circle and a red square. A blue circle and a red square. They're all the same. Whereas over here, we have individual blue circles and individual red squares, and also over here. So B and C would be considered mixtures. Which one is definitely a heterogeneous mixture? C is definitely heterogeneous. All the blue circles are on top, all the red squares are on bottom. This one could be described as homogeneous. The thing about heterogeneous, homogeneous is it's like many things, like rich versus poor. There's a continuum there. There's not a place in the middle where it's like absolute black and white, like you're alive or you're dead. There's, kind of a line there. But, rich or poor, well, there's a continuum, right? And so homogeneous, something that you might call homogeneous, if you were able to zoom in and look at all the individual particles, you might find out that it's not really homogeneous. We're just going for, what does it look like with our eyes, right? So this would be more homogeneous in the sense that it's kind of mixed up more uniformly. Mixtures can be separated, and we can separate mixtures based on different chemical or physical properties. And this is actually, there's a lot of science work that is done on this. It's like, what's an example? Like iron ore, so maybe you're trying to mine iron, right? And you get these rocks out of the earth. They have iron in them, but they've got other stuff in them too. And so you have to separate the iron from the other stuff, right? That's doing a separation. We do separations all the time, and they're very, very important in manufacturing and all kinds of stuff. So let's think about the sand and water. One way that we can separate those is a technique called decanting, and we'll do that in lab. There's a video about it. So, imagine that glass of sand water. I really should have a glass of sand water. That would be more fun. Just imaginary glass of sand water. I let the sand settle to the bottom, and then I carefully pour the water out. The water that I pour out is going to be nice, clean water, right? And what I'll be left with here is sand and a little bit of water, right? So I can separate the water from the sand. Now, getting the rest of the water off, that's sometimes a little more difficult. But that would be decanting. Another way is filtration. And both decanting and filtration depend on different physical states. One is a solid, one's a liquid. So you could also take that sand water and pour it through a coffee filter, and the coffee filter would catch the sand and the water would run through, right? So we're separating things based on their physical state. We can also separate things based on differences in chemical properties like boiling point. So this is a very simple distillation apparatus. And, you know, when people make alcohol illegally, you know, moonshiners or something, they're out in the woods and they've got this still, right? It's a distillation apparatus. So let's say we have water and alcohol in here and we want to get the alcohol out. Well, alcohol boils at a lower temperature than water does. So if we heat this mixture, the alcohol will evaporate, will turn into a gas and float away from the mixture before the water does. Now, if we do that in an open container, we lose the alcohol, which if you're trying to just get the water, that's great, but usually people want to keep the alcohol. They don't care about the water. So we need to trap it. So this is closed, and we cause this vapor to go through a condenser. This is a tube that has double walls, and you can run cold water through it. And so that will cool it down. What happens when you cool a gas? It turns into a liquid, right? It's called a condenser because it condenses the gas into a liquid, and then the liquid runs down here, and we can capture it in another flask. And so we'll get the alcohol here, and the water would get left behind. And that's separating based on difference in boiling point. We do that a lot in organic chemistry.